right, well, good afternoon. I'm Dr. James Brownlow. I work at Edwards Air Force Base. There's some contact information. So the first caveat is this is actual flight test data, but in order to get it released, it was unclassified data. I eliminated the range to a target, and I eliminated the actual units, changed them to qubits, which, if you know Greg Hutto, that's his favorite unit of measurement. Now, what is TLE? Target locator error basically is you put a pod on an airplane, you drive into a target, and that pod is helping you identify where that target is, surface to air system or a truck or something along those lines. And ideally, what we'd like to do in developmental tests is determine how well that particular algorithm pod system works. And to that end, we develop target locator error as a function of range, sometimes some other parameters. Now, okay, so here's the basic idea. TLE should get smaller as you get closer to the target. TLE basically then should be, in some sense, proportional to the range of the target. So you could think of that as a differential equation. So a change in TLE with respect to range would be proportional to how far from the range you are and what the mean offset would be. So what you see there would just be an ordinary differential equation that describes that. Now, the part that we added to explain that is no two runs are identical. So there's a random component in this. So what we're going to do is we are going to add a Weiner process to that differential equation, deriving a stochastic differential equation, which then must be solved. Let's see. So let's see. I'll skip over this one. This is basically here's the idea. All the slides have been posted, so you can read through that. I'm not going to cover all of them because I go through some of the mathematics of this, and I don't think that's appropriate here. But basically, here's the idea. We have a basic differential equation. We're going to add to that a stochastic component. The stochastic component that is a Weiner process. The derivative of the Weiner process is normally distributed. It's like a random walk, which we're using. And then you write a differential equation, which looks like in that second bullet, the dx dt is f of xt plus L of, basically what you're saying is that there's a differential equation that describes sort of how you're getting closer. And then you've included in that a random walk, which describes some uncertainty as you get closer to the target. And then what we'll be doing on that is the uncertainty is sigma times the range. And as the range gets closer, then the uncertainty gets smaller. So you decrease that as well. Now, let me get to, okay, so, well, by the way, back up here, there's a bunch of details, which I'm not going to talk about today. The problem with a stochastic process or a stochastic differential equation is the Weiner process is everywhere continuous, nowhere differentiable. So how do you do the calculus? Oh, crap, the chain rule doesn't work anymore. Now you got to go to Ito calculus to solve that. And so I've got some slides in a little bit about that, but that's basically the idea there. So you can see in the determine the appropriate form for this stochastic differential equation, the second bullet. That's the typical form. The change in target locator error is a function of target locator error and range to the target, plus a forcing function based on that random walk. Okay, and so then, well, there's a couple of models that are famous you can look at. There's the OU, which is Ornstein-Uhlenbeck model used in finance. There's CIR, which is the Cox Ingersoll Ross model, which is used in finance as well. And the only difference is including some function of range in the dispersion part of the random walk. And there's a couple other aspects of it, but let's, and then of course there's an issue, you've got to fit the data. So let me go on to basically what happened. This is a picture of the black that you see in this slide is the actual data. That's real data. And then what you see in the colors that are behind that are the simulations from a fitted stochastic differential equation. So then we would like to say then, okay, how well can we describe the system to be working? That's the whole idea. So there are a couple things we'll look at, and that would be predicted target error as a function of range to the target. The closer you are, the less range there is. There's an asymptotic distribution for that. And then that's what the red line there basically shows, what I would expect the target locator error to be as I close to target. And the blue distribution was something like 1,000 points from the target. That was some range from the target. But everything in this data set is in data point number, not range. I did that so I could get the data released. And this is basically what the total result of this thing turned out to be. I had 8 actual data runs from an aircraft, and then I used those data runs to fit the Cox Ingersoll Ross differential stochastic differential equation, and then based on that stochastic differential equation, I derived the parameters of TLE as a function of range. And in this case, it turned out that a 90% confidence interval at the target was between 4 and 18 qubits, which was not too bad. And the whole point there is that now you have some idea that can give you a reasonably good characterization of how well you're doing in terms of target location error as a function of range. And that has significant tactical implications. How close do I have to get? If you can, something like that. So the other thing is that this stochastic differential equation, if you can derive that or set that up for a particular system, you can put that in an airplane. And now you can tell the guy driving the airplane, you don't get any closer than this, you're good. Or no, you don't shoot from here, you can't get there from here. So that would be a significant improvement in deployment of a particular weapon. And that was actually, I worked on this, and then Teresa Daly from Eglin looked at it. She said, well, why don't you put this in an airplane? Oh, it's a good idea. Maybe we'll do that. And that's all I've got. I mean, didn't go into the details, but I do have the slides. They're posted. And just if you want to get involved in stochastic differential equations, start with Edo calculus. Any questions? All right. Well, thank you.